Hello everyone, I'm Meryem Le Deunf. I'm a PhD student and I work with Charles Pezerat, Frédéric Ablitzer and Nicolas Merlette on the identification of the damping provided by a foam placed on a metal plate by an inverse vibration problem. This is an industrial project between the Acoustic Laboratory of Le Mans University and the test center Cfat at Saint-Étienne-du-Rouvray, close to Rouen. Today, many solutions are used to ensure the NVH comfort of ground and air vehicles, like heavy mass, viscoelastic treatments, and absorbing foams. Heavy mass, like bitumen pads, are mainly used to reduce vibration of panels and limit structure-borne noise emissions. The objective of OEMs is to reduce the weight of vehicles, to decrease fuel consumption and reach CO2 targets by keeping acoustic performance. A possible way will be the use of trim foams to damp vibration of panels and limit the use of heavy solutions. The aim of our work is to develop a methodology to measure the vibration damping of panels covered with trim foams. To measure this, we need to create a measuring bench to characterize the influence of foam plate interface on the damping. Finite element analysis is used to determine the damping sources and drive the development of the experimental approach. An inverse method is coupled with the use of laser vibrometer to have a local, contactless, and non-intrusive measurement. The inverse method is based on the motion equation of a plate. A force is applied on the structure. If we consider an area where no forces are applied, the motion equation is equal to 0. The displacement field of the structure is measured with a laser vibrometer, and the finite different terms are calculated. Then, the structural parameters, like the rigidity and the loss factor, are determined. This inverse method is noise sensitive. To limit the error provided by the noise, a regularization of the method is used. The first regularization is the force analysis technique, or Cfat method. It relies on a low-pass filter and a 2K window to reduce the boundary effect of the filter. The second regularization is the corrected force analysis technique, or Cfat method. This method uses a natural filter of finite difference schemes characterized by the corrective coefficients. The combination of these two methods increases the frequency range of the study. The setup is composed of a suspended steel plate with a foam placed on it. Different types of interface, glued or not, are characterized. The vibrometer is scanning the area where the foam is in contact with the plate. A source excites the plate outside this measurement area. The steel plate is a complex structure with an outer and inner plate. The inner plate is the measurement area where the foam is placed. The outer plate is damped by a heavy mass to reduce the noise due to the boundaries effects. Then, the Cfat and Cfat methods are used to determine the structural parameters. The last step is to search for different contact dissipation laws of foam plate interface, not glued, glued, or partially glued. Numerical methods are used to understand the origin of the contact dissipations. The results of the structural parameters for 3 configurations are presented. The rigidity divided by the mass per unit area is in function of the frequency. The red curve corresponds to the measurement of the foam with a thickness of 11 mm glued to the steel plate. The blue curve corresponds to the same foam, but this time it is not glued to the plate. The green curve corresponds to the measurement of the plate alone. The thickness of the steel plate is not exactly equal to 1 mm, so two theoretical values of the rigidity are calculated. The dashed line is for a steel plate with a thickness of 0.9 mm, while the other one is for a thickness of 1 mm. When the foam is glued to the plate, the rigidity divided by the mass per unit area is weaker than the other configuration. When the foam is not glued, the rigidity is almost equivalent to the configuration of the plate alone. It indicates that the foam has no mass effect. The loss factor is now shown in function of the frequency. The curves color are equivalent to the previous graph. This means the red curve corresponds to the foam glued to the plate, the blue curve the foam not glued to the plate, and the green curve for the plate alone. For the red curve configuration, the loss factor is higher between 1500 to 5 kHz compared to the not glued interface, blue curve. The blue curve has a loss factor higher than the red curve between 350 to 1500 Hz. In conclusion, the foam interface configuration plays a key role on the frequency range of the loss factor. Experimental and numerical results of the foam glued to the steel plate are compared. The graph presents the rigidity divided by the mass per unit area in function of the frequency. The orange dot curve corresponds to the experimental values, and the red dashed curve is the solid model made on Actron software. The numerical and experimental results are close at high frequency. There is a rigidity change at 3500 Hz. Our hypothesis is that the effect of the foam changes with frequency. At low frequency, the foam is viewed as an added mass, and at high frequency, it is an added spring. On this figure, the damping is in function of the frequency. The experimental results are given by the orange dot curve. The Ross-Kelvin-Ungar model is the blue curve, and the Actron solid model is the red dashed curve. The numerical values are in good agreement with the experimental results. The damping is increasing in the same frequency range as the rigidity, also shown in the previous graph. Viscoelastic effects of the foam are the origin of the damping, in the case of a glued interface. Experimental and numerical results, this time of the foam not glued to the steel plate, are compared. The graph presents the rigidity divided by the mass per unit area in function of the frequency. The orange dot curve corresponds to the experimental values, the red dashed curve is the solid model, and the green dashed curve is the porous model made on Actron software. The numerical model is close to the experimental values at high frequency. But at low frequency, there is a gap between numerical and experimental results. On this figure, the damping is in function of the frequency. The experimental results are given by the orange dot curve. The Ross-Kelvin-Ungar model is the blue curve. The solid model is the red dashed curve, and the porous model is the green curve. The orange curve follows the porous model at high frequency. Damping mechanisms are defined for a not-glued interface. At high frequency, the porous effect of the foam contributes to the damping. However, at low frequency, the origin of the damping is unknown. That is why a temporal method is in progress. In conclusion, we have created a measuring bench that reduces the influence of the noise at the boundaries, and a protocol to quantify in frequency the structural parameters of a biliar structure with different contact at the interface. Preliminary numerical results seems to indicate that the damping induced by a glued interface is due to the viscoelastic effects of the foam. In Outlook, we want to understand the origin of the damping when the foam is not glued to the plate. Our assumptions are that the damping might be due to the dry friction, impact, or viscothermal effects of the foam. A temporal method is in progress to improve the correlation between numerical and experimental results. Thank you for watching. If you have any questions, don't hesitate to contact me at this address.